Hello friends, welcome to our third lecture on probability.
Hello, people.
Um, as usual, I'd like you to turn on your cameras. For some reason we have only 11 people right now. I hope that more people would come. So,
Margarita said that she will be late.
what's wrong, Vlad?
Margarita said that she will come a bit later.
Well, okay, at least one person, but you're supposed to be 30 and now there are 11.
Why
Okay,
30?
no problem. So let's first briefly remind ourselves what we had in the previous lecture. So we spoke about the concept of probability, and we defined a probability using some axioms. So basically, the probability measure is a function, and this function allows us to transfer. Oh, sorry, guys, I need to have a pause for 1 second. So we define the probability measure as a special function which allows us to map or to represent some events, and we spoke about events in our revision of the set theory, into some numbers, and we put some restrictions on these numbers. So first of all, the whole sample space and the probability of that sample space is not cannot be so should be equal to 1. Any probability of any event in that sample space must be non-negative, either 0 or positive. And also we define that for two disjoint events, probability of their union equals to the sum of their probabilities. So then we still didn't said anything about the rules how to calculate this probability. We took it as, let's say, some assumption that if we have, for example, 4 events or 4 elementary events into the sample space, and we want to calculate the probability of one of them, we simply divide 1 by 4, and that's how we calculate this probability, assuming that those events are equally likely. So this is, again, take into account that this is an assumption. It is not given by some rule. This is an assumption that we believe that all these events or all these elements are equally likely. That's the only chance that gives you this way to calculate probability. And then we spoke about the simple algorithm of calculating the probability. And out of this algorithm, the most, let's say, important step is to count how many elementary events are inside the sample space and how many elementary events are included into the event of interest. Why? Because when we calculate the probability of some event, we need to sum over the probabilities of a sample points inside that event. And sometimes it might be a problematic. So if in this case you can easily construct the number of events in the whole sample space. So we had this example and the total number was 10. It's not a problem. But if you have something more extended, for example, if you are looking for a probability to, well, to get some particular card out of 52, so then you need to know about this 52 something. And if you have something more extended, of course, you need to do some tricks in order to calculate the total number of sample points in the sample space. Or here, if you have 12 boys, 18 girls, and the teacher selects one boy and one girl to act as a representative, so we need to know the number of all possible arrangements of these boys and girls. And of course, it is not possible to construct all these arrangements by hand. You just want to calculate how many distinct arrangements are there. And we define this multiplication principle, which is the basis for calculation of this number of sample points. So multiplication principle says that if you have m outcomes in one particular experiment and then n outcomes in the other particular experiment, then you just multiply these two numbers in order to find out how many possible outcomes are in two experiments. If you have more than two experiments, then you apply this extended multiplication principle and you proceed in the same way. So do you have any questions regarding this multiplication principle? Because today everything that we are going to discuss will be based on this multiplication principle. So I have it also here as a repetition. Okay, so if there are no questions, unfortunately, I think you didn't have an exercise session on this topic, so we will have some exercises here during our lecture. So let's proceed. So now, as I said, based on this multiplication principle, we will build some extended methods for counting. And so the name of the lecture exactly about counting. So how can we count the total number of sample points in some particular experiment? So there are some special terms, and the first term is permutations. So what is a permutation? It is an ordered arrangement of R objects, and the main, let's say, word in this definition is an ordered arrangement. So what does this mean? It means that we are interested in some particular order of elements that are inside the event. So we will see the example, and I hope you will understand what's that. So we may have two different options about this ordered arrangement. For a set of size n and a sample of size r, there are n to the power of r different ordered samples with replacement. So this is one statement. And these permutations from n are permutations from n, which is calculated like n times n minus 1 times n minus 2 times and so on. And we usually use this short formula n factorial over n minus r factorial, different ordered samples without replacement. So let me show you an example, and then we will come back to this definition just to understand better what is this about. Look, we have 5 children, and we want to know how many ways we can line up these children. So it means we can arrange them from first to the fifth. So how can we calculate this number of possible lines of children? Of course, this is an ordered arrangement. Why? Because each child is distinct object. And we really care. So suppose we have A, B, C, D, E. Somehow their names start with A, B, C, D, and E. So who is the first? How many possible options do we have to put a child on the first
5.
place? 5. Then, if the first child is here, then we have how many residual options?
4.
4. Then we have 3, then we have 2, and then we have 1. So this is exactly an example of this, of different ordered samples without replacement. Why? Because we cannot take one child and put this child into 2 places, right? So we kind of, it's not possible. So that's why we are using this approach. So it's 5 out of 5. And yes, we calculate it in a way that it's 5 times 4 times 3 times 2 times 1, which is n factorial, which is exactly 5 times 4 times 3 times 1, and n minus r is 0 factorial, which is 1. Exactly, so we can build 120 different lines. Those who wrote their answers in chat, you were correct. So all of you. Another example. Suppose that we have 10 children and we are choosing 5 out of those 10. Once again, how many different lines are possible? So, out of 10, first we pick one child. How many possible options do we have to pick out of 10?
10.
10. Then after we selected the first child, we have 9. Then we have 8, then we have 7, then we have 6. And then we stop, right? Because we need to choose only 5 kids. And once again, we do care about their order. So who is the first, who is the second, because we want to line them up. It's like, you know, in your classes for physical culture, so it matters who stands first, who stands second. So we have something like this. This is gonna be the permutation, 5 out of 10. And then we calculate it in this way, as a shorthand notation, we are using this formula. So basically, this is not necessary. As I said, this is only the simple way how we can write this calculation. This 10 by 9 by 8 by 7 by 6. But if you understand the principle, basically you don't need these factorials and don't be afraid of having them. This is just a nice short way to write the same the same expression. By the way, I hope you know what is factorial, right? So this is the product of natural numbers from 1 to the number that is given here. So 10 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. And in the denominator, we have 1 times 2 times 3 times 4 times 5. And when we divide the first factorial by the second factorial, we exactly have this residual 10, 9, 8, 7, 6. That is here. Any questions about the permutations? So these two examples are the examples of permutations without replacement. With replacement, it's even simpler. You just multiply n by n by n by n that much times. So how many repetitions you have. So we will have that example a bit later. Any questions here?
No question.
Conditional will be преобразование, yes?
Oh, Vladimir, I don't know what is the Russian word for this. So
Okay.
try to open some Russian book on probability theory and find it. I don't remember what's the Russian term for that. There are, of course, but I studied this in Russian like 20 years ago, and I really don't remember what's the Russian word for this. Okay, so one more example for you. It's a bit more extended. So in some states, license plates have 6 characters. Like in Russia, for example, we have license plates with 6 characters, 3 letters, and then 3 numbers. If all sequences of 6 characters are equally likely, what is the probability that the license plate for a new car will contain no duplicate letters or numbers? The only thing here that we need to understand which alphabet we are using, right? Because we need to know how many characters are possible there. So let me see. Yeah, so we have 26. So let's assume that we are using Latin alphabet. There are 26 distinct characters, and of course 10 digits, right? Because if we are speaking about numbers, so it's 0, 1, 2, 3, up to 9, so we have 10. So try to calculate this yourself. How would you find so first of all, you need to start with the total number of all possible license plates. And then what is the probability that the license plate for a new car will contain no duplicate letters or numbers? So we need to find the subset of those license plates that do not have a repetition.
I think the 26 letters plus 10 numbers and choose the arrangement of 6 and it's promote 36 and 6. I think it's so big.
Well, the number is going to be large, of course.
Yes.
But you need to
Yes, I
calculate it.
calculate it. I in the checks.
So once again, let's assume that we are using Latin alphabet, 26 letters. Okay, so let's start with the first step. If you remember, or if not, I will remind you, we need to apply this simple algorithm of probability counting. So it's where is that? It's here, right? So first the experiment is the so we are selecting one license plate, and one simple event consists of kind of 6 characters, 3 letters, 3 digits. So that's our experiment. So second step here is to list the simple events associated with the experiment. So we need to calculate how many possible license plates are there. And in order to do this, we need to count how many possible permutations of these 6 characters can we have. So you can tell how we calculate the total number of license plates. Where should we start with?
I think there are 26 of the letter.
Okay, 26 letters can be
So-
on the first place. Then on the second
So
place,
it's
we also have
26 and 3.
26.
We need 3 letters.
Yes, it means that how many possible arrangements of these letters do we have?
Oh, so yes, 26, then 25.
No, letters can repeat. If we want to count the total number of license plates, letters can repeat. It is possible to have AAA 000, for example. It is possible to have BBB 111. It's possible. It's totally okay for license plates, and
Then
these
it's
two license
26
plates are
too.
going to be different. So how we can calculate the total number of plates? It's 26. So try to apply the multiplication principle.
It's 26, 26, and 26.
Okay, and then how many digits do we have? From 0 to 9, we have 10 digits.
About 10 numbers. Yes.
So 26 times 26 times 26, and then
10, 10, 10.
no, times 10 times 10 times
So
10.
it can be
So here.
18,576.
So you have it here on the screen now. Look. So 26 times 26 times 26 gives us 26 to the power of 3, which is 17,576 different ways to choose the letters. So we have these 3 letters, and there are 17,576 possible arrangements of those letters. And you exactly care about their order. So ABA is different from AAB, and BAA is different from ABA, for example. So that's why when we started speaking about permutations, I said that permutations is an ordered arrangements of objects, right? And in this case, we have sample with a replacement, because we can use the same letter several times. I can use A, and this is totally fine. So we have this first type of permutations. So, okay, then we have 3 numbers or 3 digits, and 10 digits, and the total number of their arrangements is 10 to the power of 3, so which is 1000. And we apply multiplication principle. 26 times 26 times 26 times 10 times 10 times 10 gives us this 17 million possible plates, license plates. So our omega, the sample space, consists of all of these possible sequences. Now look, second step. We want to calculate how many license plates do not have duplicate letters or numbers. What it means? It means here I want to calculate how many license plates are possible without replacement. If I used A, for example, letter A once, I cannot have it second time. I should have something like ABC or ABD or ABE, but not AAB. AAB is not possible in this particular question. I don't want one letter or one digit to repeat. So how should I proceed in this second step? Exactly the same way how we did it here and in a previous slide. I need to reduce the number of possible options by 1 on each next step.
I think it's P26 3.
Yes, that's correct. For letters, it's correct. And for numbers, it's gonna be permutations 3 out of 10, right?
For numbers, I think it's P103.
True.
Oh,
So it's here. 26 letters on the first step, 25 on the second step, 24 on the third step. So we have these 15,000 ways to choose the letters without duplication. And 10 times 9 times 8, 720 ways to choose the numbers without duplication. So in total we have 11 million non-repeating sequences. So we have in total that much license plates, 17 million, 17 and a half. And without repetition, we have 11 million, a bit more than 11 million. So the probability of an event A, which is the probability to get one license plate without a repeating characters, is 64% or 0.64. So I hope that this example gives you an idea what is the difference between permutations with replacement and permutations without replacement. So with replacement means that you can use the same element several times. Without replacement means that you cannot use an element which was used only once. And the whole idea of permutations is such that you really care about the order of these elements. So those are ordered samples. Once again, ABC and BAC are two different orders and two different events. And the different story is when we speak about combinations. So combinations means that we are taking R objects of n at a time. So it's a number of subsets, each of size r, that can be formed from the n objects. So what is subset? In subset, we do not care about the order. So ABC and CAB are two exactly the same elements. This is the same element. ABC, BAC, CAB is the same element. Why? Because we care about subset. We care only about the elements and not about their order. We can order them in any direction. It's gonna be still the same element. That's the most important difference between combinations and permutations. And we denote these combinations with C and taken R, or we usually use this, which is called binomial number, R out of n. So these two notations are equally used, and later on in this course, in statistics, in econometrics, we will be using these combinations in different environments, let's say, for different reasons. So how to calculate that? It looks similar to the permutations, and basically it is the way how we calculate permutations, but we need to reduce the number of elements by the number of repetitions by r factorial. Why? Because, as I said, ABC, CAB, and BCA, for example, are the same element. That's why we reduce this number by division by this R factorial. That's the difference between permutations and combinations. So, an example. If you remember, we had, if not, I will remind you. In this lecture, we had this example. We needed to select 2 applicants out of 5, and we wanted to calculate the probability that we have at least the best and 2 poorest, or at least 1 of 2 best. So basically, we've been interested in particular events. But first of all, we needed to calculate how many possible sample points do we have in the sample space. So we build this manually, 1, 2, 1, 3, 1, 4, and so on. And we calculated that that was 10. Look, this is exactly an example of combinations. Why? Because we want to select 2 elements out of 5, and we don't care whether it's 1, 2 or 2, 1. Look, we had only 1 element here, 1, 2. Because I don't care which order I'm selecting these 2 candidates. I just care that I selected first best and second best. Or it can be second best and first best, I don't care. I still have these 2 people. And this is the example here. And if you want to calculate the total number without this manual construction of possible options, then we will do this. We will calculate these combinations of 2 out of 5. And I'm using this. So 5 factorial over 2 factorial times 3 factorial. And I will get exactly the same 10. So how this works? Look, if I'm choosing 2 candidates and I care about the order, so we know how to do this. It's kind of, so how many? 5, right? I have. So it's 5 times 4, which is 20. But then look, for me, 1, 2 and 2, 1 is the same. So it means that 2 options out of those 20, so those 20 options, they are duplicated 2 times. So that's why I divided by 2 in order to get the number of non-repeating elements here, in order to get this 10. Exactly the same application of the multiplication principle, all the same. So just now I kind of do this in the reverse way. I'm reducing the number of elements, knowing that there are some repetitions occurred because of repeating elements. Here is an example for you. Based on that same example about applicants and about best or not best applicants. So here you need to think about the following. If an event A denotes the event that exactly 1 of 2 best applicants appears in the selection of 2 out of 5, you know something about the second. If you select 2 applicants and only 1 is the best, 1 of 2 best, then the second one comes from 3 who are the least, let's say, professional. So try to think about this. How would you approach this problem? how would you calculate the number of sample points in this A such that you have exactly one of two best applicants in your selection. So it means that basically we have this. You can calculate it manually, so it's either this 1 3 or this 1 4 or this 1 5 or 2 3 2 4 or 2 5. So 1 2 3 4 5 6 possible options are there. But try to calculate this without looking at the sample space. Try to calculate this applying the multiplication principle and what you know about combinations. So you know the correct answer. It's going to be 6. Try to find this 6 applying combinations. So let's try to do this together. So because probably it might be a bit difficult, I just somehow gave you a chance to think yourself. So look, let's denote an A, the number of sample points in A in this event. And this an A equals the number of ways of selecting one of two best times the number of ways of selecting one of three low-ranking applicants. So this is a hint for you. So we apply multiplication principle. We know that there are two elements in our selection. One element is one of two best. This is the combination of 1 out of 2. Another element is the combination of 1 out of 3 least let's say least professional candidates. So and then we multiply these two numbers. So here I calculate the combinations of 1 out of 2. Here it's going to be 2. And I calculate the combinations of 1 out of 3, which is 3 factorial over 1 and 2 factorial, which is just 3. And then I multiply 2 by 3 and I have 6. Right, so we have the same 6 as we counted manually from that previous example. So here I want to draw your attention not to the calculation of combinations. I want to draw your attention to this. So you need to be, whenever you calculate some probability, whenever you count the number of occurrences, you really need to be careful about the definition of your event. So look, here we know that we want to have exactly one of two best applicants. It means that this element 1 and 2 should not be here, because in this element we have two best applicants together and we want to exclude this element out of our selection. So that's why we introduce this additional information. We introduce this information that, well, if I know that there is going to be exactly one best applicant, then the second applicant for sure must come from 3 least professional applicants. And that's how I have this second element and the number of these least professional applicants. So this is very important. And in many different occasions, we really want to introduce this additional information based on the event that we want to know. So we know that the total number is 10 and the probability is 6/10. This is simple. So the most interesting part is here. Are there any questions about this example?
I didn't understand, like, why is there 2 1 in M?
We have two best applicants, I mean, like first and second place, and we are selecting only one of them. That's why we have this 1 out of 2. And here we have 1 out of 3. 1 out of 2 best and 1 out of 3 least best, let's say, of worst. Okay, one more case when we want to apply multiplication principle and we want to apply something similar to what we discussed right now. This is called grouping into classes. So we have n objects and we want to group these objects into R classes, and each class has ni elements inside this class. And as you can, so let me give you an example when we can do this. So suppose there are, so now there are 19 students from your group, and I want to randomly select, let's say, 5 students in one group, 10 students in other group, and 4 rest students to the third group. So I want to kind of group you somehow. So first question, do I care about the ordering? No, because for me it matters only that these 5 people are in the first group. I'm not particularly interested who is the first, who is the second, who is the third, right? It's not lining up. It's just a collection of, it's a subset of students. So second, of course, when I select 5 students into the first group, I have less possible options to the second group and to the third group. So that's why I divide the whole, that factorial by factorials of number of elements in each group. Right, so that's how I calculated this possible number of ways how I arrange people into groups or some other objects into groups or classes. So here we have an example, something similar to what I said. So we have 7 members in a committee, and we need to divide those 7 members into 3 subcommittees. As I said, we have a group of students, and I want to divide this group of students into 3 different subgroups. And we know that one subcommittee must contain 3 people, second 2 people, and third 2 people. So we can do this in 210 possible ways, and the calculation goes as follows. So 7 factorial over 3 factorial, 2 factorial, and 2 factorial. So basically, look, this is the combination of not combination. Probably it's not a good word here. This is an extended application of permutations, because if I form only one group, I will calculate 7 factorial over 7 minus 3 factorial, right? So it's going to be this. But if I form several subcommittees, I need to exactly do this, to divide by the number of elements in each subgroup. So that's how it works. So here I have some additional explanation about the difference between permutations and combinations. So just a simple example on this. So suppose we have a collection of elements A, B, C up to Z, so Latin letters, for example. So we take 3 elements and register their order. So possible options are ABC, ACB, BCA, ZYX, and so on. So the order matters. So how these letters appear in my selection, it matters. Like in the example of car license plates. And these are permutations. Don't be confused. Whenever we take 3 elements and we don't care about their order, we don't care which element is the first, which is the second, which is the third, we just care that exactly these 3 elements are selected, then it means that ABC, CBA, BAC are the same elements for us. We don't care about them. And that's why possible options are ABC or ABD or BAZ or XYZ, but we don't want them to kind of to be rearranged. So all of them are same for us. So these are combinations. So basically, whenever you count some number of possible events, you need to first ask yourself whether you care about their order or not. If order matters for some particular situation, then yes. If order doesn't matter, then you use combinations. In most of the cases, I will just give you some clue. In most of the cases, we don't care about the order. If I select 5 students out of 19, I don't care about the order. But if, for example, I select, there are 2 different situations, let's say. If I want to have 5 students, let's say, to work in a group on some, I don't know, study project, then I don't care about their order, right? So there's going to be a combination. But if, for example, in the next class, it's just an example, it's not a task. If, for example, in the next class, I would ask you to make some presentations, and I would like to know who is the first, who is the second, who is the third, then I'm gonna do permutations because the order would matter. It matters for me who goes first, who goes second, who goes third, and so on. That's the difference. If I really care about the order, then it's permutation. If I don't care and I want to know only the collection of students, then not. Chancy, what's going on there? So you decided to have a rest. You're killed by probability counting. Okay, do you have any questions? So now on the next 2 slides, I have some exercises for you. Just in order to apply these principles, try yourself how this works. Do you have any questions about combinations, permutations, grouping? Okay, so if not, then basically my lecture part is finished, and now we have several exercises for you to try how this works and to discuss if you have some difficulties or questions here. We have something like half an hour now for this part. So this is your task. So please, whoever has an answer, write in chat or try to tell. Yeah, so this is just to warm up. You have 6 flights in one segment, 7 flights in the other segment. This information, if a passenger takes flights on separate days, just tells you that you can combine any of 6 flights from the first segment with any of 7 flights from the second segment, right? Because they don't coincide, just to give some sense of real life. And yes, the total number is 6 times 7, which is 42. Just simple application of multiplication principle. So the next. Well, I see that many people did. That's just 3 factorial. This is the permutation because the order matters here, and permutation without replacement, because if we use some first operation, then we cannot use this twice. Perfect. So the next. So I see that many people did the answer. So let's see. So 4 appetizers, 3 salads, 4 entries, and 5 desserts. So we can just apply a multiplication principle. So there is nothing about combinations or permutations. So that's going to be 240. Nice. So these are simple. Now let's move to something more interesting in the next slide. So we have 2 answers, 3, 4. Other opinions about the answer? That's too fast. Yeah, so now 9 million. Why 9 million, not 10 million? Because the first digit cannot be 0, right? So we select from 9 options at the first step, and then out of 10 options on all of the other 6 steps. So that's why we have it like this.
Like she need to be one of these prepositions or what?
Well, she is just about the personal director, if I got your question correct. I mean, so there is a director. So it's kind of the modern English style. Whenever we speak about somebody, we write not he but she. Well, something like, we cannot be gender neutral in this case, but you know that like in English there are no genders for nouns, so that's why we usually write something like she. So consumer is she, personal director is she, and something like that. So we have 10 engineers, and out of those 10 engineers we need to fill 3 distinctly different positions. So this is a bit tricky. So now we have different answers. Some people think that this is 720. Some people think that this is 3 to the power of 10. So let's try to wait for more answers. So there are even more, 9 times 19 to the power of 6. Isn't it about the first exercise? Zhao Ruxuan. So, okay, who can tell what is this about? Number 2. Is this about combination or is this about permutations or neither of them?
Permutation,
Why do you think that this is permutation?
because engineers that has to be for position are distinctly different.
So this small piece of information gives you exactly a clue what you should apply here. Because if we don't care who goes to which position, there is gonna be a combination. But we do care. So there are like 1, 2, 3 positions, and we really care who goes to the first position, who goes to the second, who goes to the third, which means that we are using permutations, and it's here. Yes, so it's 10 times 9 times 8, which is 720. So those who have this answer were correct. And those who wrote that this is 3 to the power of 10, unfortunately it's not. Why? Because this is not what we wanted. We didn't want to form 10 entries out of 3 with replacement. So 3 to the power of 10 would be something like, okay, I am trying to randomly select one of those 3 positions, and then I register their order in 10 of a sequence of 10. This is something completely different. Okay, number 3. So this is a bit more difficult. Only 2 people answered. Okay, let's wait for more answers. Maybe there are gonna be different options. Guys, please write the answers, because whenever you write some formulas, for me it's not. So I don't understand what was there A, 3 and 3, for example. So what is this about? So now a lot of people did its answers. Yeah, so this is about grouping into classes. We have a number of objects and we need to group them into 3 classes. We need to send them into 3 airports, and well, it's 9 factorial over 3, 5 and 1 factorial, which is 504. Well, guys, you are stars. This is very nice that I see that you understand what's going on. I hope that more exercises you will solve during your exercise sessions. We will try to prepare something tricky for you, since you are so good with these simple exercises. Do you have any questions regarding the material? Do you want to clarify something?
I have one question from the first exercise. Like I don't
First here
understand
or first
where.
here?
No. Yeah, the first. I don't understand where we took 10 by 6.
Look, we have 7-digit telephone number. It means that we have 7 places, and 7 times we need to pick the number. So first must be not 0, It means that it's 1, 2, 3, 4, 5, 6, 7, 9. We have 9 possible options to pick the first digit. Then on the second digit, we have 10 possible outcomes. Why? Because it's 0, 1, 2, 3, 4, 5, 6, 7, 9. We have 10. And then on the third place, on the fourth place, on the fifth, sixth, seventh, we have the same. So basically it's going to be 9 times 10 times 10 times 10 times 10 times 10, which means 10 to the power of 6. Arina, did I answer your question?
Thank you. Yeah, thank you.
Okay, perfect.
I'm sorry, I have a question. Can you please send this PDF file somewhere to
Well, that's gonna be
through,
after your
please?
questions. Thanks for asking. I was going to tell you about this. Yes.
Okay, thank you.
One more question. On the last slide, the second exercise.
This one.
With yes, with the personal director. So if we could, if we were to choose not distinctly different, but just any one, what formula would we use? Like combination?
You need to divide the 720 by 3 factorial. Yes. So it's going to be 720 divided by 6, which is how many? 720 divided by 6. If there are no distinct positions, then it's 120.
Oh, okay.
Combinations, yes.
Thank you.
That's exactly the difference, whether the order matters or not.
Okay, so if order matters, we don't divide. If it matters, then we divide.
Yes, exactly. So the relation between permutations and combinations is shown here. You either divide by r factorial or not. More questions? Okay, so now some organizational thing, and after my introduction, you will have more questions. So finally, congratulations! This week we have a page for our course, so probability. I put here books. From these books, you're going to solve the exercises on your exercise sessions, and so you can use one of them or like all of them if you want to read on some particular topic and if you want to know more about the probability. So all of those 3 are more or less nice and they are not that difficult. Probably this Hog is more formal. These Wackerly and Rice, they are very understandable, very clear. So I have put here lecture 1 notes, lecture 2 slides, so lecture 3 are going to be also here. For exercise 1, I've put here solutions. These solutions are made myself, so they may be somehow different to what you had with Klim during your exercise session, but so in most of the cases there must not be many differences. So since the page is created recently, I didn't have time to make the first home assignment for you on this topic, but it would appear in a short time. I will let you know. So probably after the weekend, you will have the home assignment on this set theory. And then depending on your success on exercise session, probably on the probability counting, there is also going to be another home assignment. So now we have the same as for microeconomics. The only thing I forgot to do is to enroll you to this course. So just give me a second. I will do this, and you should find yourself on. You should find this.
I'm sorry. So we'll have opportunity to make homework on probability just after the weekend.
Second. Okay, perfect. Now you are here. Now you can have an access to this page. once more, could you repeat your question, please?
Yeah. We will have opportunity to make our homework after the weekend.
I think so. It depends on how busy I am and how fast I can make these home assignments. Because for microeconomics, for me, it's simple. I've made this course last year and I don't spend too much time on your home assignments preparation and so on. I just turn it on and that's it. For probability, for me, it's more time consuming because I need to make these home assignments and it takes time, you know, to have the home assignment with the whole explanations of the solution that you can see after the home assignment and so on. So I really hope that you will have the first home assignment after the weekend. If I can make it faster, you will have it faster. But don't worry, I will give you enough time, something like 1 week, maybe more, and I will let you know in advance. You don't need to update this page every hour waiting for the home assignment. Don't worry, I will let you know in that WhatsApp chat. Just now you have an access to all these materials and whatever matters, I will also put it here. Okay, more questions?
Can I ask about microeconomics? About home
Maybe
assignment.
during microeconomics, just because it can matter for other students from management. Just
Okay.
you know, because we have other people and probably it is the important information for them as well. So keep your question
No, I just about my home assignment.
About home assignment.
About my ISN.
Mm-hmm.
Yeah.
Mm-hmm. So go on.
Will you check our photos about exercise?
So let me tell
Can you
about
do it?
this
Yes, because
when we start our class on microeconomics, because as I expected, it matters for everyone. I expect to receive this question from many people. So I will tell you about this on the next lesson, okay? So about probability, any questions? Okay, then thanks for your attention. We are a bit earlier today. You have a bit longer rest. So see you in 24 minutes on the microeconomics class. Thanks for your participation. It was really nice.
Thank you too.
See you.
See you.